Okay, so in class we started our notes by looking at the bottom of page 3 to finish that out. And this first slide that has these definitions that are already written in your packet, it's not really something that we'll test you over, but it kind of gives us context for what we're doing following this. So just be aware that there is an international system of units, which is based off of the metric system that all scientists use as our standard. It's important to have a standard unit so we can all talk and communicate in the same language without having to do as much translation, because our actual languages have enough translation going on. And if you're not sure why that's so important, look into the 1999 Mars orbiter disaster that happened. It all happened because scientists weren't all using the same units, and there was some confusion that happened, and we lost that orbiter. So when it comes to these units, there are slightly different types of units. Basically, not all units are created the same. And once again, this isn't something I'm going to test you on, but understand that there's something called a base unit, like length, which is something that you can directly measure. You can take a ruler and measure the length of a textbook or a piece of paper or anything. But there's also a type of unit called a derived unit that you can't actually measure directly, but you can calculate it from some other base units. And an example of that is volume. And you might think, well, Mrs. Gunter, we have things to measure volume, but we really don't. And let me explain. If we have a cube, in order to measure and figure out its volume, we don't have a volume measuring device. We would have to measure the length, width, and height of this cube or rectangular prism, and then do our length times our width times our height to find our volume. And you might be saying, like I assumed, that we have graduated cylinders that have those lines, those tick marks in them, that we could just put that cube into some water that's in a graduated cylinder, see how much that water goes up, that's the volume. But still, this graduated cylinder that we'd be using is not an actual measurement. What scientists and really the engineers that designed these did is they found the area of that circle, that opening, based off of the radius, and then they actually calculated the height, the distance between each of those tick marks to give us that volume. So even though we have a nice measurement unit here, it's still a derived unit because it's based off of other base units that were measured in order to get that measurement device. So once again, not something that I'm going to test you on, but just be aware there are differences between some of these units. Now, this is the most important part of this page 13 units section, is making sure we know what are the appropriate units to be using and measuring in the lab, and what should we put on all the numbers when we measure them. Even though it might seem like a pretty short unit of time, seconds is our standard unit for time. Even if we have a long reaction that lasts all day, if we're timing that reaction, we're going to measure it in seconds, and then we could turn it into minutes or hours if we needed to, but keeping those seconds would actually give us the most significant figures there. Then our length unit is our standard meters, like you're probably expecting, is our basics for the metric system. Mass, if we put something on a scale, it's going to give us that mass in grams. And volume, you might say milliliters. Once again, all of our measuring devices does have milliliters on it, but those milliliters are really just a smaller form of the liter. So the liter is really our standard volume for liquids, but milliliters is going to be what we see a whole lot. So that's going to be kind of our normal unit, but it's not the standard international unit. Now, the volume for a solid is commonly relayed in meters cubed, and this kind of comes back to that cube I was talking about measuring. If we did have that volume, we would find it by measuring the length, width, and height in meters, and when we multiply all three of those meters measurements together, meters times meters times meters gets us meters cubed. So, cubic meters is that standard. Now, this one's going to seem weird, but the amount of substance that we have physically, like the number of molecules of water or sodium that we have reacting, is going to be measured and quantified in number of moles. So moles, I know, sounds like an animal, and it is an animal, but moles is also a unit for amounts. So I could say, oh, 2 moles of water are going to react with 1 mole of sodium in order to produce some stuff. So mole is a unit we're going to use. If you look at that abbreviation there, we can't really abbreviate it by much. All the rest of these get significantly shorter, down to a letter or 2. But our moles, M is already taken by meters, MO is month, so MOL is the shortest we can make it, and that's really more than half the length of the original word. So it's not much shorter, but it does work. And then hopefully you do know that our standard temperature in all sciences is going to be Celsius. So from here on out, we need every single number in this class to have the appropriate unit on it. And if you're ever not sure, you can either come back here and check what units belong with which measurements, or ask. I always want to help you know and be confident in that answer. So now let's move on to page 14. And this really is the most important part of these notes that we did in class. And we're going to spend probably the next 30 minutes working out about 10 problems. And I've posted all of the answers to every problem on this page on Canvas, so you can check your answers at any point in time. And if you start to get the hang of this, feel free to pause the video and try the next few problems. And if your answers are coming out right, you don't necessarily have to watch the rest of the video to watch me working through them, or maybe just click through and check your setup in order to make sure you understand the process. But it's this process which is so important. It's not the actual answers. None of the problems on this page are really that hard to do, and several of them you could probably work out and figure out without using this dimensional analysis process. But this process is going to be following us through chemistry all the way through Unit 12. We're going to be doing some dimensional analysis basically every unit from here on out. And it's going to help us solve much, much more complicated problems than what you're seeing here and now. But if you don't learn this process now, when the problems are kind of sort of easy, once we get to those harder problems, you're just going to be lost, and it's going to be a struggle the rest of the year. So it's really, really important that we do dimensional analysis to solve every problem on this page, which is going to be kind of a railroad tracks looking situation. And you'll see several examples of it, and I'll work through every single problem on the page. But that's the process that we're focused on, and every single number, both in those structures and our answers, needs to have a unit on it to be getting credit for that process and the work that you're doing. So if you're watching this because you were absent and you haven't been able to do these notes with me in person, if you start getting lost, once again, go ahead and just pause the video, come in. I would much rather you spend that same amount of time asking me questions as I work through these with you directly than to have you spend all of your time lost, confused, just copying stuff down and not understanding it. This is a really important process, so do what you gotta do to get it right, because the sooner you do, the better off you're going to feel about this, and the easier this class is going to be all year long. So let's go ahead and get to it. What is dimensional analysis? Well, it's really a process of using conversion factors to convert between units. Well, what's a conversion factor? A conversion factor is a fraction form of a unit equation. And technically, that's the first and only thing you need to write down in your notes from this slide. But because conversion factors are based off of unit equations, I'm going to help you understand what is a unit equation and how do we turn them into conversion factors. So if any of this is useful, I'd encourage you to find a place to write it down before we move on to that next slide and fill in that next blank, because this is the meat and potatoes of what we're doing here. So what's a unit equation? This is kind of a long, complicated sounding definition, but it's something like 12 inches equals 1 foot, or this example, 2.54 centimeters equals 1 inch. It's really just an equation, so we got an equal sign in the middle of it, with different unit numbers on either side, things that are equal to each other, but that are in different units. So these unit equations are usually used to help us make conversions, things that we either know or things that we could reference or Google and look up. and use them to do a conversion. But we're going to be using these in a specific way. We're going to turn these equations into conversion factors. We're going to turn them into fractions. And we're going to do that by taking each side of that equation and putting it over the other side. And as you might be able to tell, because there's two different sides, every unit equation can be turned into two different conversion factors depending on which side you choose to put on top. So here you can see that same unit equation has been turned into two different conversion factors. The first one has our centimeters on top and inches on bottom, and the second one has inches on top and centimeters on bottom. And so these are two different conversion factors from the same unit equation that would be used in different circumstances. But that's really all that we're doing. Once we know the unit equations that we need, then we can use them. It's about turning them, so that one side is over the other, and that's it. Now, why would we choose to do it one way versus the other? Let me give you a little bit of a preview into this dimensional analysis thing. So like I said, with dimensional analysis, we're going to be doing some kind of train tracks looking sort of conversion. And we don't normally start with it all written out, but I kind of want you to see this here. In every problem that we're doing a conversion, we're going to have some kind of given, a number in the problem. So let's just imagine I have some number of green stars, and I want to convert them into purple flowers. So during this process, we're going to use a couple of unit equations in order to do that. And the two unit equations I'm going to tell you about is that 5 green stars equals 3 smiley faces, and 7 purple flowers equals 2 smiley faces. Now, the way we're going to set up and work dimensional analysis, and the way that I know how to change and rearrange these unit equations into conversion factors, is by looking at what's called the diagonal rule. And the diagonal rule tells us that whatever units we have on top, usually are given in that first bracket, that first kind of starting point, needs to be the same units on the bottom. So we get these diagonals matching so that we can move forward. What we're really doing is canceling out those green star units in order to get closer to the purple flower units that we want. So the first equation I'm going to use is the one that has green stars in it, and I'm going to make sure to put it so that those 5 green stars can go on the bottom to follow that diagonal rule. And since I'm choosing to put that half of my equation on the bottom, that means that my 3 blue smiley faces is going to fill out the top. Notice how this is the exact same stuff here in this conversion factor over the top of each other as what we see in that first unit equation. I've just chosen to put the 3 smiley faces over the 5 stars. I could have chosen to do it the other way, but that wouldn't have helped me in this specific problem because it wouldn't help me follow our diagonal rule. So if I'm still wanting to try and get rid of those smiley faces and get to our purple flowers, then in this next bracket down at the bottom, I would need to have some kind of blue smiley faces here in order to cancel out my blue smiley faces that are on top. And if I'm wanting to get to those purple flowers, then that means I'm putting my 2 blue smiley faces on bottom, and my 7 purple flowers can fill in the top. And if all of these other units have canceled out, if I have the same things on top and bottom, they've canceled out and gone away, the only units that are left are purple flowers. So that's the diagonal rule. That's how we know how to flip our unit equations into each of these conversion factors. And for each problem, there's really only one correct way to flip it. So you have to keep checking that diagonal rule. And of course, we need to have the units in our dimensional analysis because those purple flowers and the blue smiley faces and green stars are how we're deciding how to flip these equations and turn them into conversion factors. So without units, you're going to be lost. You have no idea how to set this stuff up. So, like I was just talking about and explained with all of those other examples, when we're doing these conversions with dimensional analysis, the unit to be canceled is going to be placed on the opposite side of the conversion factor from where it started. And because our given is going to be written on the top side of the line, usually for us, that opposite side is the bottom. So these next two slides are, once again, stuff I don't need you to write down. I'm going to real quick just kind of explain a couple of things. They're not examples in your packet, kind of like that last example. I just want you to see how we set up and solve some of these problems before you actually have to copy it down and get it. And this first slide really is just an FYI. You're going to see me use what's called the guess method a lot. So you're going to see the words GUESS written in my problems a lot, or structured on my slides. And it's just a way of solving problems. It's not something I need you to do, but if you start getting stuck in these problems, going through this guess method could help you figure out where you're getting stuck and solve that problem. The G and the U are pretty simple, but it's about reading, finding the question, and finding that given information and what you're trying to solve for. What are we looking for? Kind of frames the problem. What units am I starting with? When do I know that I'm done? What units am I ending with? And then the E step there is for writing out equations. And because dimensional analysis is all about taking those unit equations and turning them one way or the other into those conversion factors, sometimes it really does help to write out those equations so you know what your choices are and you can kind of visualize turning it one way or the other. Now, those first three steps are not technically required. G, U, and E are really just about setting the stage to make sure you can be successful in your problem. But every single person needs to write down, once I get to those last two S steps, those are the parts that I've made sure you have enough room in your packet to fit in. And you have to show, like I was saying earlier, that dimensional analysis setup to get any points on any of these problems. So, and then of course the answer, the solution, has to be written down if you want credit. So that's why you're going to see problems like this where I have GUESS or just ESS, because that given and the unknown I tend to find and highlight and mark in my problem. So I'm going to work this problem, which is a little more real life problem than just, some fun smiley faces and stars and flowers. So you get an idea about what a real unit conversion is like with real units. But once again, you do not have this in your packet and you do not have to write it down. I'd rather you watch this process happen than to write it down and not understand it because you are so focused on getting it written down. We've got plenty of other problems for you to work out on your own. So, if I read through this problem, it starts off with my question. How many M&Ms would we burn off while running a full marathon? And that question actually has both my given and my unknown in it. Of course, the unknown is sometimes easier to find. It's asking how many M&Ms would we burn off? But my given is that I'm running a full marathon. I'm going to be running 26.2 miles. Everything else in this problem is just context or a unit equation that we can use to do a conversion. It's known that an average person burns 310 calories for every 3 miles they run, so I just take out some of those words, put an equal sign in there because those two things are equal. 310 calories, running 3 miles. And then there are 140 calories in a serving of M&Ms, which is 32 pieces. So 140 calories in 32 M&Ms. Pretty simple. This should be all we need to answer this question. Now, as we start to do our dimensional analysis, usually we start with an empty line. I just draw the line because all of our numbers are going to go either over or under this line as we're building it out. And the first number we always write on the line is our given. So 26.2 miles, coming right down, number and unit on top of that line. Then generally the next thing I do is draw a line after it because we're going to separate that given from each of our conversion factors that we're going to be putting here. But because I have these animated popping in, that'll show up when I put my next conversion factor in place. So if we're trying to figure out, which equation is going to help me turn these miles into M&Ms, we need to look at our units. The units on my given are miles. So what I know is diagonally down from that, I need more miles. I've got to cancel out these miles. So when I'm looking at my equations, I'm going to use my green equation because it's the only equation that has miles in it. So I know what equation I'm using, but we still have a choice to make because that equation can be turned into two different conversion factors. But like the diagonal rule was helping us with already, I know I need my miles to be on the bottom, not the top, because I need them to be able to cancel out the miles that we already have here. So miles, those are the same unit on that same diagonal. So we're looking good so far. And technically, if I stopped at this point and calculated this answer, that'd tell me how many calories I would be burning off in a marathon. But that's not what I care about. I don't want calories. I want M&Ms. So we're going to keep moving forward. Now that I have calories, I want to cancel them out. And this is when that blue equation can help us, because that's the equation that has calories. Technically, the green one does too, but if we use that green equation again, that would only get us back to miles. The blue equation can both cancel out our calories and get us to M&Ms, which is what we want. And that's one of the reasons why that guess method is so helpful, keeping in mind my unknown is M&Ms. That's where I'm headed. That's the direction I should be going, can keep you on track. But once again, with this blue equation, we have to turn it into a conversion factor, and we have two options. But we want the option that's going to cancel out our calories and get us M&Ms. So we're going to choose that second one this time, putting calories on the bottom. So we're canceling out the calories we got, and now we've got M&Ms. If we check all of our diagonals here, miles matches with miles, calories with calories, and what we're left with is what we wanted. So even though people are really uncertain, this is a new process, and you want to ask before you put it in your calculator and find an answer, if you check those diagonals and the diagonals match and what you want is at the end up on top, then I'm confident your answer is correct. Go ahead and put it in the calculator. And the way we put it in the calculator is by multiplying all of the numbers that are on top of this big long fraction line. So the units have canceled, but those numbers are still there. We haven't canceled out the numbers. So you can put this all into your calculator all at once. 26.2 times 310. Don't push enter, just keep going. Times 32 divided by 3 divided by 140. And then push enter at the very end. And that should get you 618.819047. And hopefully your sig fig instincts are saying, that seems like a lot of numbers to write down. I don't think we need to write that many, but there's a lot of numbers here. Which ones do we use to round? And the great thing about dimensional analysis is, for the most part, we just look at the given. That given was the one measurement that we took. Everything else is generally an exact number in conversion factors. So just focus on the sig figs of your given and make the answer sig figs match. So because our given had 3 sig figs, we're going to round our answer to 3 sig figs, which means our answer is 619 M&Ms. So hopefully this process isn't that hard. It's a little bit weird, but once again, if you have questions about any part of this example or any of the others, please come and ask, because it's really just a pattern that you have to get used to and go through this process of building up each bracket from the bottom using that diagonal rule in order to get the units that you want. Okay, let's go ahead and start working some examples in your packet. So these are not going to be quite as complicated as some of the ones I've been showing you, but I still want you to use dimensional analysis to solve it so you can see and understand this process. So this first problem asks us to take 358.3 inches and turn it into feet. So that number in my problem is my given, and what it's asking us to find is our unknown. So I'm trying to turn inches into feet. Even though it doesn't give us any equations, any information, hopefully we know something about inches and feet. 12 inches equals 1 foot. And that should get us straight from inches to feet. So if we're going to use this dimensional analysis process now, we're going to start with a line, and we're going to write that given on top of the line. It is always our first number, and of course we need units on that number. because now, as we move into using a conversion factor to turn these inches into feet, we've got our unit equation waiting for us right here, and because I've got inches on top, that means I've got to have inches on bottom. If I'm looking at my equation, that means 12 inches goes on bottom. If that went on bottom, what fills in the top half? Why, the other half of our equation. Keeping that conversion factor together, just like in equation form, just feet on top of inches. And now, if we check our diagonals, they match. We've got the units we want. We're ready to calculate. And in our calculator, we can put in this 358.3 times 1 and then divided by 12, and that will get us our answer of 29.853 repeating. And if we look at our given was 4 sig figs, so we want to keep these first 4 sig figs of our answer, which means that our real, true, final answer is going to be 29.86, and of course getting the unit of feet onto that answer. So, like I said, you probably could have done this on your own and just divided by 12, which I don't mind if you know that you don't need to push the times 1. If that isn't going to affect the value, you don't have to push the times 1 button in your calculator. I still need to see this 1 foot here to show that completion of our conversion into feet. Now with this second problem, we're going to be taking our answer from the previous problem, so 29.86 feet, and we're going to turn those feet into yards. And we already have an equation given to us here, so we can jump straight into setting up our dimensional analysis and putting that 29.86 feet on our line. And now if we're trying to decide how to use this conversion factor, because I have feet on top of my dimensional analysis bracket as my given, then I need to put the 3 feet on bottom in order to keep that diagonal rule true. Always has to be true in our problems. And then we can put 1 yard. YD is the abbreviation for yard if you need to shorten that down. And that should get us there. That's going to get us our answer. And so if we take 29.86 and divide by 3, then we get 9.953 repeating. And this right here is 4 sig figs already. So all we need to do is add our unit, and that can be our answer. Hopefully this isn't feeling too crazy, but once again, come in with questions if you're getting lost and confused in these problems. We're going to do number 3, which is technically question 1 and 2 together. Instead of stopping at feet, we want to turn these 358.3 inches, which is our given, into yards. And I know it says directly, but that just means in one go, putting it in the calculator all at once. I still want us to use the same conversion factors that we did in questions 1 and 2. I just want us to use them together. So I want to show you how this can evolve from a single-step problem to a 2-step problem. And I know you've already seen me work out a couple of 2-step problems, so hopefully this isn't too difficult for you. Of course, we start with our given 358.3 inches. And just like when we started the first problem, since we've got inches on top, I know I need inches on the bottom of that next bracket. That means this first equation is going to help us get there. And as we put that 12 inches on bottom and fill in the 1 foot on top, this looks exactly like our question 1. But unlike question 1, we're not done yet. So we need to keep going and keep converting because I want yards, not feet. So I put another vertical line, and now I'm focusing on canceling out my feet and turning them into yards. And that's where my second equation is going to come in, making sure to put the 3 feet on bottom, 1 yard on top. I'm there. I've got yards. My diagonals match, so I'm going to get what I want if I plug this into my calculator. And It wasn't that much harder than doing one conversion at a time. Just got to keep in mind, what are we looking for? What's our unknown? And keep going until you get there. Now, interestingly enough, if you plug this into your calculator and get an answer out, initially that unrounded answer is 9.9527 repeating is technically looking a little different than the answer that we had in question number 2. But once we round that to 4 significant figures, that 7 is going to round our 2 up, we get 9.953, which is exactly the same answer as what we got before. So even though it might seem a little bit different, what this is telling us is that there's no significant difference between doing it in one step and doing it in 2 here. So sig figs are helping us understand, even though it looks a little different, it's really kind of the same process. So hopefully if you've gotten this far and you're not too confused to give up and just come in for help in person, let's make it a little bit harder. Let's do a slightly longer conversion, and a little bit more words for us to deal with here. So I'm going to highlight this problem as we read it, because there's a lot going on here. Evidently, we're going to market, and before the use of money, people bartered for goods that they needed. 25 chickens could be traded for 1 pig, and 10 pigs could be traded for 1 cow, and 2 cows could be traded for 3 horses, and we wanted to figure out how many horses could be exchanged for 1,500 chickens. So there were a lot of numbers in that problem, a lot more than in the previous problems, but there's only one that was our given, and that was this 1,500 chickens. Remember, the given is usually part of the question, and I can tell they're trying to ask us how many horses. That's our unknown, is horses. And what are we trying to get horses from? Chickens. So evidently, I've got 1,500 chickens at home. I want to trade them in for horses, and I assume this problem is me planning ahead and trying to figure out, is it worth me getting all these chickens to market? Can I get enough horses to make it worth my while? Or should I keep saving up and bring in more chickens later? So that's our given here. We'll need that for our dimensional analysis in a moment. But I'm going to take these other numbers and turn them into our unit equations, because every other number in here was telling us what was equal to something else. So first off, 25 chickens equals 1 pig. I'm going to have to make up some abbreviations for these words, because I'm not going to be able to fit it all in if I had to write all of those words out. And then 10 pigs can be traded for 1 cow. And then 2 cows could be traded for 3 horses. So, with all of that set up, let's go ahead and make a line for our dimensional analysis and get our given on top of that line. So 1,500 chickens is what I've got. But I don't want chickens. I want to get rid of my chickens and try and get some horses. But unfortunately, no one is trading chickens straight for horses. So the only way I can get rid of my chickens is to trade them for pigs. And if I've got chickens on top of my line in this next bracket, I'm going to have to put chickens on bottom, which means that that 1 pig is going to go on top. So if I stop now, that'd tell me how many pigs I could get. But I don't care about pigs. I want horses. So we're going to keep trying to cancel out these pigs and get closer and closer to horses. Well, no one's trading pigs for horses either, but they are trading pigs for cows. So I can use this green equation now, making sure, because pigs were on top, I'm going to put the 10 pigs on bottom, which means 1 cow fills in the top part there. But we're still not done yet, because I don't have horses. So we're going to keep going, and luckily I can trade those cows for horses. And I'm just going to make sure, since cows is on top here, that they go on the bottom there, so we can end up with horses at the end up on top. And if you're thinking that looks too easy, check your diagonals. All of these match, and we're left with what it was asking for. So this is set up correctly, and I want everyone to try plugging this into your calculator. I know some of these other ones were easy and maybe you hadn't, But even on your phone, I want you to see if you can put all of these numbers in together and get out the answer to this problem. It should be a single-digit answer to this problem. So pause the video real quick. If you need a hint to help, remember we multiply all these numbers across the top and we divide by any numbers that are on the bottom. So you should be plugging in, or have already plugged in, 1500 times 1 times 1 times 3, and then divided by 25, divided by 10, and divided by 2. And you can plug all of that into your calculator all at once, push enter at the very end, and hopefully you got 9 as your answer. If you didn't, make sure to talk to me in class. I want to help you figure out how to put this all in your calculator, because even if you end up with a beautiful setup, that's not going to get you full credit unless we can get the correct answer out of that dimensional analysis setup. Now here, let's talk a quick moment about sig figs again, because we had 2 sig figs in our answer here, so we need to make sure to get 2 sig figs in our answer over here. Sorry, 2 sig figs in our given, so 2 belong in our answer. And of course, a unit. I was using H before for horses, but because I have the room, I'll go ahead and write out the full label. So hopefully this is getting easier and easier the more you set it up. But once again, if you're starting to feel just completely lost, stop the video, come in, let's work a few problems together. This next problem, I'm not going to work out at all. I didn't work it out in class either, unless people were completely lost, then I would help walk them through it individually. But this is when people started to kind of be able to figure out what to do for themselves. So I'm going to highlight this problem and help you kind of get started on it a little, but I'm not putting the dimensional analysis on the screen. Nothing that would actually get you credit for this problem. So do the best you can and come in for help if you need it. So we're going to be trading cars instead of animals now, and a car enthusiast developed a system for placing values on cars. In their system, 1 Maserati was worth 3.5 Porsches, and 1 Porsche was worth 5 Jeep Wranglers, and 2 Jeep Wranglers were worth 15 Ford Pintos. We were trying to figure out, if I collected 225 Ford Pintos, how many Maseratis would they be worth? So what I'm going to point out here is that what we've got is 225 Ford Pintos. That's our given. And what we're trying to find, our unknown, is how many Maseratis would they be worth. Everything else here is an equation, and I would encourage you to make some abbreviations here as well. And I'm going to help you write out some equations with my abbreviations. They're just the letters of each of those cars' names. Equals 15, not 5, Ford Pintos. All right. So these are the 3 equations you're going to need to use. And when you're setting up your dimensional analysis down here, make sure you start with your given and then pay attention to your units and that diagonal rule. If you do this right, your answer should come out to be 1.71 Maseratis. Now, don't let that answer hurt your heart. I promise no one's taken any chainsaws to any Maseratis to get those decimal points, but it's an important number to know. If I wanted at least 2 Maseratis, that means I gotta save up some more Ford Pintos. If I was happy with just getting 1 Maserati, because who wouldn't be happy with 1 Maserati, then that means, hey, I can get my Maserati and still have some cars left over. So we keep those decimals based off our sig figs, and that's important to know that sig figs amount, even if we're not ever going to end up with exactly 1.71 Maseratis. So go ahead and work on that problem, and when you're done, we have a couple other problems that I am going to work through, but none of them are as hard as that last problem. So if you were able to get those Maseratis, I really would like for you to pause or stop the video here and work out the next few problems, see if you can get these answers. If you can't, then just click forward until I'm working out the problem that you need help on. Now, we need to make a quick change and addition to number 6 here. We need to put a decimal at the end of that given. I really don't want you to have to round that down to 1 sig fig. I'm never purposely going to have you round something down to 1 sig fig. So, just put a decimal there, make it 3 sig figs so that my answer with 3 sig figs makes more sense. And yeah, let's go ahead. I'm going to work these out, but like I said, pause the video here if you're kind of getting it. If you're not, then I might consider coming in and asking for help instead of just copying down these last few problems. So, working number 6 and making sure that we have that decimal there at the end of that number, we have all of our equations already given to us in our problem. And so our given, what we've got is 500 grams, and we want to turn that into ounces. So ounces is our unknown. Now, if we put that 500 grams on our dimensional analysis line, looking at our conversion factors, the only one that has grams in it is this first one, grams getting turned into pounds. I don't want pounds, but it's the only thing I can do to get where I need to go. So I'm going to use this equation, making sure to put the grams on the bottom in order to follow that diagonal rule. Means that now 1 pound can go on top. But I don't want pounds, so time to get rid of them. I'm going to use this second equation here, making sure to put the 1 pound on bottom, and then I can put 16 ounces on top. Looking at everything, my diagonals match. I've got the units that it was asking for in the problem up on top, so we're ready to calculate. Now my unrounded answer is 17.621145, and it keeps going. But if I only want to keep 3 sig figs, like we talked about, because I made my given 3 sig figs, then I'm just going to keep the 17.6. The 2 does not round my 6 up. So 17.6 is my final answer. Ounces is the unit. In this next problem, we're trying to work a classic chemistry problem. But even though you don't really have the greatest understanding about what moles are, we can turn moles into grams using some simple equations. 1 mole of water is 18.02 grams. So that's our equation, and our given is that we have 2.33 moles of water, and our unknown, we just want to get that to grams. And since we have a mole to gram equation, it looks like we're going to be able to get there in one step. So we're going to start with those 2.33 moles. And then since moles are on top, I'm going to put the mole part of my equation on the bottom. And then the 18.02 grams. And that's it. My diagonals match. Grams is what I got. If we multiply to find our answer, my unrounded answer is 41.9866. I want to keep 3 sig figs just like my given, but here my 8 is going to round my 9 up, and unfortunately my 9 is then going to round my 1 up. So this is going to become 42, but we can't leave it just like this 42, because that's just 2 sig figs. So even though the rounding ended up changing a lot more numbers, we still have to keep that 0.0. That 0 is a significant figure because we got a decimal there. And so that is our correct 3 sig fig answer with units, of course. And then finally, question 8. How many seconds are there in 24 hours? We're back to problems kind of like the first couple where we didn't give you any equations in the question, but you should know a little something about minutes and hours and seconds that could get us to do this conversion. So our given is 24 hours. We are looking for seconds. What equations do you know about hours and seconds? Well, if you're saying there's 24 hours in a day, you're right, but that's not going to help us get closer to seconds. So hopefully you also know that 1 hour is 60 minutes. Okay, that's great, but that's not getting me all the way to seconds. So what else do we know? Well, 1 minute is 60 seconds. Okay, you can kind of see how we're going from hours to minutes with this first conversion, and then from minutes to seconds with the second conversion here. We can kind of connect the dots between our hours and our seconds, and it's going to take 2 conversions to get there, but we can see that we have all the equations that we're going to need in order to get there. So let's start setting it up. Of course, our given is the first thing we write down on our line. We've got hours here, so these hours are going to be the ones we have to use. 1 hour on bottom, that means that 60 minutes goes on top. But I don't want minutes, so we keep going. We cancel out those minutes with our second equation and turn them into seconds. So here we just need to take our 24 times 60 times 60, and our raw unrounded answer is 86400. That's 3 sig figs though, and our given is only 2. So we are going to round that down to 2 sig figs. And this throws some people off sometimes, but obviously our second sig fig, the one we're keeping, is this 6. And keep in mind that 6 is in the thousands place. We can't just round this number down to 86 and say, oh, that's the same number. It's just rounded. So significant figures sound weird to people. So let's just change the wording. After we found that second sig fig, this 6 is in the thousands place. So let's round this number to the nearest thousand. Is it closer to 86,000 or 87,000? Hopefully you agree it's closer to 86,000. So we're going to basically replace that 4 with a 0 to keep that place value, keep this number being about the same value, but get rid of that third sig fig. As long as we don't put a decimal at the end, that's still just 2 sig figs and not 5. So when we round numbers off, if we have a big number like this, then any numbers between the sig figs we're keeping and the decimal place, even if the decimal place is kind of imaginary and invisible, we have to replace those numbers with zeros to keep that place value. So 86,000 seconds is 24 hours. So that's where we're going to call it for now. Technically in class we might have gone on to questions 9 and 10 at the top of the next page, but I'm going to record those separately because some classes got to them and some of them didn't. So if you still need those examples, go ahead and watch the next video that's on this page, but otherwise you're done with the notes that we got done in class, and that's the kind of basics of dimensional analysis. And questions 9 and 10 have some little twists that are a little weird, but nothing harder than what you're doing here. Just something that I want you to get some guidance through. So watch that next video if you need it, or come in for help if you need more help with these problems on page 14.